Welcome to this introductory training video on Spring AI and the modern AI application stack. We will break down key concepts like generative AI, large language models, or LLMs, and how Spring AI makes them easy to use in your applications. Spring AI provides a consistent, familiar, and convenient Spring-style developer experience for building applications powered by artificial intelligence. It is designed to simplify the development of applications with AI capabilities, aiming to avoid unnecessary complexity. Throughout this training, we will explore the core components and advanced patterns that allow you to build sophisticated AI-driven features, such as chatbots, voice assistants, and data analysis tools. We presume you have zero prior knowledge, so let's start with the very foundations of how Spring AI serves as the crucial abstraction layer in this new world of intelligent applications. This foundational knowledge will be key to understanding how applications integrate with powerful external models and services. This comprehensive overview will set the stage for diving into the specific technical components that compose the modern AI engineering landscape, starting with the primary role of Spring AI as the abstraction layer connecting your Java application to the vast ecosystem of AI providers. We will keep the language simple and direct, making complex topics accessible for absolute beginners. Let's get started now by defining Spring AI's fundamental purpose. This entire session will be a step-by-step journey through the key concepts you need to succeed. Spring AI is essentially a set of libraries within the Spring framework, designed to help Java programmers use the most popular artificial intelligence or AI technologies available today. Think of it as a universal translator and adapter that sits between your application and the powerful AI services outside. Its primary function is to serve as a client abstraction layer, handling all the complex details involved in sending requests, called prompts, to many different AI providers. This abstraction is crucial because it gives you a portable service experience. This means that the code you write remains consistent, whether your application is using a model from OpenAI, or Anthropic, or Google, or another provider like Hugging Face or Mistral AI. The core benefit here is avoiding being locked into a single vendor. If you decide that a different model or service is better for your needs, you can switch providers simply by changing a configuration line, rather than having to completely rewrite your application's core integration code. Spring AI handles the intricacies of the underlying REST application programming interfaces, or APIs, ensuring that developers can focus on building value through innovative features, rather than wrestling with technical minutiae. This focus on simplification and consistency is the main contribution of Spring AI to the modern AI application stack. This integration focus makes advanced AI accessible to millions of Java developers worldwide. This diagram illustrates the core role of Spring AI in the modern application architecture. On the left, we have your Spring application, containing your core business logic. This application needs to communicate with external AI services, which are represented on the right side. The central component, highlighted in orange, is the Spring AI abstraction layer. This layer acts as the consistent interface for all interactions. Instead of writing custom code for OpenAI's specific API, and then different custom code for Google's API, your application simply talks to Spring AI. Spring AI then translates that request into the format required by the specific large language model, or LLM, provider you have selected, such as OpenAI, Anthropic, or Google. This setup achieves the goal of portability. If you want to swap from using OpenAI to using Anthropic, you only change the configuration within the Spring AI layer, and your main application code remains unchanged. Following on from understanding Spring AI as the central abstraction, we must now look at the primary component used to talk to the AI brain itself, the chat model. LLMs are specialized algorithms designed to learn patterns and insights from huge datasets, allowing them to create text, images, or other outputs. The P in GPT, which stands for Generative Pre-trained Transformer, indicates that these models are pre-trained, transforming them into general developer tools that do not need an extensive machine learning background to use. In Spring AI, two core components manage this communication: the chat model interface and the chat client class. The chat model defines the basic method for sending prompts and receiving responses, acting like the core library. Building on top of this low-level interface is the chat client, which is often compared to a more advanced utility layer. The chat client offers a fluent application programming interface, or API, and provides advanced structures like advisors to enhance interactions, for example, by managing past conversations or augmenting the input with extra documents. Spring AI ensures you can easily connect to many leading chat models, whether they are running in the cloud, like those from OpenAI or Google, or locally, using systems like Ollama. This class diagram outlines how Spring AI establishes a unified approach to large language models. At the foundational level is the model interface, which is extended by the chat model interface. The chat model interface requires a common call method that takes a prompt as input and returns a chat response. Specific implementations, like OpenAI chat model or Anthropic chat model, fulfill this interface contract, ensuring consistency regardless of the underlying vendor technology. The chat client sits atop this structure, offering a simplified and more sophisticated way to interact with the model. When you use the chat client, Spring AI handles the complexities of selecting and communicating with the specific chat model implementation you have configured. This layered structure is the mechanism that delivers portability. Therefore, the key point is that the chat model interface creates a standard framework, enabling seamless switching between different model providers without breaking your application code. What are the two main components Spring AI uses to connect to an LLM, and what is the relationship between them? Now that we know how to connect using the chat client, let us discuss how to talk to it using prompts. A prompt is the input provided to the large language model that directs it to generate the desired response. The quality of the output depends greatly on the quality of the prompt you provide. In Spring AI, a prompt is not just a simple string of text. It is captured in the prompt class, which contains a collection of individual messages. Each message is assigned a distinct role, which helps the model interpret the input correctly. The two primary roles are the system role and the user role. The system role defines the overall context, purpose, constraints, and behavior for the model. For example, you might tell the model, "You are a helpful customer support agent," or classify movie reviews as positive, neutral, or negative, only returning the label in uppercase. System prompts are effective for maintaining a consistent tone and setting global parameters across many interactions, especially in multi-turn conversations. The user role, on the other hand, is the direct request or question from the user, which forms the core task of the prompt. Mastering the composition of these messages is referred to as prompt engineering, an iterative process essential for eliciting specific and accurate responses from the AI. This diagram illustrates how a prompt is constructed within Spring AI before being sent to the LLM. The prompt class, shown in the center, is the container for all instructional content. It receives input from two primary sources: the system message, shown in red, which defines the model's overall behavior, rules, and context, and the user message, shown in green, which contains the specific question or task requested. The combination of these messages forms the complete prompt that is passed to the LLM or chat model. An optional but important component is the output indicator, which specifies the desired format for the response, such as asking for JSON. The LLM processes all these inputs and returns the generated output, usually as text. Understanding the distinction between the system message and the user message is fundamental to effective prompt engineering. What are the two core message roles within a Spring AI prompt, and what is the primary purpose of the system message? The core roles are system and user, and the system message sets the model's persistent behavior, context, and constraints. While prompts guide the content, they don't always guarantee the format, which is a major challenge for developers. Since an LLM's response is fundamentally a text string, even if you ask for JSON, the response might contain extra words or formatting issues that break your application's ability to read the data. Structured output solves this problem by enforcing a strict output format. Spring AI provides powerful utilities to implement this pattern. One key utility is the bean output converter. This converter takes your Java class, or bean, automatically generates a formal JSON schema based on its structure. This schema is then inserted into the prompt sent to the LLM, effectively telling the model, "You must generate a response that perfectly matches this exact structure, with no extra text or explanations." When the AI returns the JSON response string, the same bean output converter automatically deserializes, or converts, that string back into a usable Java object. This capability is critical for reliable integration with downstream application logic. By using this pattern, you gain type safety and reliability, ensuring that unexpected output from the model doesn't cause errors in your application. This sequence diagram demonstrates the multi-step process for achieving structured output, such as turning an AI's response into a Java class. First, the Spring application uses the bean output converter to automatically generate the necessary JSON schema from the desired Java class structure. The application then sends this schema, often replacing a placeholder-like format, along with the user prompt to the AI model. The AI model, receiving the strict instructions of the schema, generates a valid JSON string as its response. Critically, the application then passes this raw JSON string back to the bean output converter. The converter's role is to convert this string into an actual Java object instance that can be used directly within the business logic of the Spring application. This complex interaction, handled internally by Spring AI, guarantees that the developer receives reliable, structured data instead of fragile, unstructured text. What challenge does structured output solve, and what Spring AI component helps achieve it? It solves the problem of unreliable, unstructured text output, and the bean output converter helps by managing the schema generation and object deserialization. To build intelligent applications that use your private data, we first need a way to translate human language into something a computer can understand mathematically. This is the role of embeddings. Embeddings are generated by specialized models that take a piece of information, such as a document, a sentence, or even an image, and convert it into a dense vector, an array of floating point numbers. Crucially, These numbers are designed to capture the semantic meaning and relationships between data points. If two pieces of text have similar meanings, their corresponding vectors will be numerically close to each other in the vector space. This allows for semantic search, where you search by meaning, not just keywords. When an application needs to store and quickly search millions of these vectors, it uses a vector store. The vector store keeps both the numerical vector and the original document content. Spring AI provides easy abstractions for interacting with these vector stores, supporting popular technologies like Postgres with the PG vector extension. This capability forms the absolute bedrock for integrating private data into AI applications, leading directly to the retrieval augmented generation pattern we will discuss next. This diagram visualizes the flow of transforming human-readable data into machine-searchable data, which is essential for grounding applications. The process starts with a document, or piece of text data. This is fed into the embedding model, shown in orange, which mathematically converts it into a high-dimensional vector. This vector, represented here as a set of numbers, is a numerical representation that captures the document's semantic meaning. This vector is then stored in a specialized database known as a vector store, shown in blue. The vector store is specifically designed to perform very fast similarity searches. When a user query is input, it is also converted into a vector, and the vector store quickly finds the stored documents whose vectors are numerically closest, implying they have the most similar meaning. This entire mechanism is the engine enabling contextual knowledge search in an AI application. What is the purpose of an embedding, and where is it stored? An embedding is a numerical vector capturing the semantic meaning of data, and it is stored in a vector store. Retrieval augmented generation, or RAG, is arguably the most important pattern for developing production-ready enterprise AI applications. LLMs are limited to the knowledge they were trained on, meaning they cannot answer questions about real-time data or your company's private documents. RAG overcomes this by linking the LLM to an external knowledge source, such as the vector store we discussed previously. When a user asks a question, the application first performs a similarity search on the vector store to find the most relevant document chunks. This step uses the vector embeddings to match the meaning of the query to the meaning of the documents. The retrieved information, known as context, is then inserted into the prompt that is sent to the LLM. This technique is sometimes called prompt stuffing. By providing the correct context directly in the prompt, you constrain the LLM to answer only based on the facts provided, which vastly improves accuracy and reduces incorrect or hallucinated responses. Spring AI makes this workflow simple through the use of an advisor, specifically the question-answer advisor, which automatically handles the retrieval and prompt modification process for you. This flowchart details the step-by-step process of retrieval augmented generation, RAG, facilitated by Spring AI's advisor feature. The process begins with the user query, which is intercepted by a vector search mechanism managed by the question-answer advisor. This advisor queries the vector store, which holds your private knowledge base. The store returns the retrieved relevant context documents, which contain the factual data needed to answer the query. This data is used to create an augmented prompt, meaning the original query is stuffed with the context before being forwarded to the LLM. The LLM, constrained by the provided facts, then produces a grounded answer. This entire flow ensures that the final response is accurate and sourced from your specific data, thereby solving the problem of LLM knowledge limitations. How does RAG enable an LLM to answer questions about proprietary data, and what Spring AI component supports this? RAG retrieves private context from a vector store and stuffs it into the prompt. The question-answer advisor manages this retrieval and augmentation automatically. Generative AI applications are no longer limited to generating text. Multimodality represents the next evolutionary step, reflecting how humans naturally process knowledge across multiple modes of data input, such as vision, audio, and text simultaneously. Multimodal models can understand and integrate information from various sources. For example, you can send a model both a photo of a recipe and a text query, asking for the ingredients. Spring AI supports this through the message interface, which can handle media attachments like videos or images using the media type. Beyond chat, Spring AI provides specific interfaces for specialized audio tasks. The transcription model offers a unified API for speech-to-text transcription, converting audio files into text. Conversely, the text-to-speech model allows you to convert text into natural-sounding speech, which is crucial for applications like voice assistants or narrating written content. These interfaces provide the same portability benefits as the chat models, allowing you to swap audio providers without modifying your application code. We have now covered all the core components needed to build a fully modern intelligent application. This stack centers around the Spring application, which uses Spring AI as the consistent client to interface with LLM providers. For persistent memory, the stack includes databases that store conversation history, often managed by Spring AI's chat memory repository. For custom knowledge, the vector store is integral, supporting RAG workflows. The framework's production-minded ethic means it supports crucial features for enterprise deployment. These include built-in observability features via Micrometer for monitoring application health, support for creating fast, efficient GraalVM native images, and the utilization of virtual threads. Furthermore, Spring AI enables the creation of sophisticated AI agents that can perform complex planning, such as implementing the chain of thought pattern, which forces the model to reason step by step. For seamlessly integrating existing business logic, the framework supports the Model Context Protocol, or MCP, allowing your internal services to be securely exposed as tools that the AI can call. This holistic approach ensures developers can build AI features that are not only powerful and accurate, but also ready for the enterprise environment.